So for something to get filtered at the glomerulus, it would need to get through the capillary, the GBM, and the podocyte. So let's zoom in on this picture to get a better sense for how that works. So the first layer is the endothelial cell. And now I'm going to draw it a little differently from how it was drawn before, because it actually has these holes in it. As we said before, that was actually not a lie. It does have these holes in it, and these holes have a special name. They are called fenestrae. Fenestrae, which comes from the Latin word for window, so they're like little windows in the endothelial cell. And if you were to look at one of these endothelial cells face on, what you would see is literally all these little holes speckling it everywhere. And this is not normal for an endothelial cell. It's only in the kidney that you'll find these fenestrae. And that's precisely because in the kidney you want to squeeze out a lot more fluid than in other tissues. And then the next layer is the GBM. And the GBM is mostly composed of collagen, which is a protein, and proteoglycans. Now, you may not have heard of proteoglycans. Proteoglycans have a protein core and then lots of little sugar chains coming off of that protein core. So you've got the proteo part, that's the protein, and the sugars coming off it, that's the glycan part. And then the last layer here is going to be the foot processes from the podocytes. Between these foot processes, we have little spaces that are sometimes called slit pores. Sometimes they're called filtration slits. So here, let's just write slits, little slits between these foot processes. And what's amazing is that to make these little slits even smaller, the kidney has little proteins that span across between these foot processes. And we won't go into the names of those proteins, there's many, but it's quite amazing to what extent the kidney makes these spaces small. Now what you really need to understand about this is how these three layers prevent a protein from being filtered. And there's actually two ways that this is done. The first is size. So proteins might be too big to get through, and usually they'll be too big to get through this part. These slits are probably the smallest thing that the protein would have to fit through. And the second way that proteins are kept out is by charge. One of the most common proteins in your blood that you really want to prevent from getting out in the kidney is called albumin. And albumin has a negative charge. Not all proteins have negative charges, but albumin does. And it turns out that the kidney uses this charge to keep albumin from getting filtered out. And actually it does this at all three layers here. So these endothelial cells have negative charges, and that's because of little glycoproteins that they express. The basement membrane, the GBM, has a very strong negative charge, and that is because of these proteoglycans that we talked about. So the glucose chains here have a lot of negative charges on them, and that makes the GBM negatively charged. And then finally, these little foot processes are negatively charged as well. So the result is that all three of these layers repel negatively charged proteins like albumin because negative charges repel each other. So you might ask, well, okay, so albumin is kept out, but what about something that was a small protein and that maybe had some positive charges? And actually, you'd be onto something, that a protein like this would have a much easier time getting through these three layers. And so actually some proteins do get through, but it turns out that this system for blocking them is still effective enough that less than 0.1% of the proteins in the filtered fluid that comes through actually get through themselves.